SwayamPrabha. Digital India. Educated India.
Okay, welcome to this lecture. Last lecture we stopped after doing, if you recall, we did the jump conditions at the interface, and we did the continuity for, or the mass conservation at the interface, and we concluded that for no phase change, the velocity in phase 1 and the velocity in phase 2 and the velocity of the interface all have to be the same. If there is of course phase change, then you have alternative relationships, which is basically this. Okay. Now, let us go to the momentum equation. So, the momentum integral equation for a control volume which has got two phases separated by an interface is given by this equation form. Let us look at each of the terms over here once again. What we have done like last time is that we have added that AI and we have subtracted the same. Okay. We have added it and we have subtracted it. So, it is essentially the same thing that we did in our continuity equation. Okay. So, what we have done is that we have added the stress at the interface and we have subtracted the same out. Similarly, for the flux term, that is the convective term, okay, what we have done is that we have added the momentum flux at the interface and we have taken the same out. Okay. So, these are the only two things that we have done. Now, the next procedure is basically to convert this to a volume integral. Now, in the volume integral, once you do the transformation, okay, as we know the volume, all these things can be transferred to the volume integral, these portions in these brackets which I am highlighting, they can be all transferred to the volume integral. So, this is what you get after you do the volume integral of the same. Okay. And the right hand side term that you see over here, it is basically the interface terms. So, the stress at the interface and the corresponding flux at the interface, okay, the momentum flux and the stress. Okay. Now, recall the original momentum equation written in the differential notation. This is the original momentum equation, right. Okay. Now, in the original momentum equation, this was the term, this is applicable for any phase, right. So, therefore, if we substitute this back into this particular equation, we get this as a result of that. Okay. So, here what it says is that the shear stress, the total stress at the interface and the momentum flux at the interface has to be equal to 0. That means, this is this integral equation has to be satisfied. Now, as we know earlier, since the integral portion is equal to 0, right, this entire integral is equal to 0, the integrand, which is basically nothing but this also has to be 0, because it has to be valid for any sized and shaped, okay, control volume. Okay. So, the size shape does not really matter, it can be as small as you want. So, the integrand becomes equal to 0, that means that there are two stress terms and two flux terms corresponding to each phase. Now, if the reference frame velocity equals to the velocity of the interface, like in the case of your momentum expression, it is equal to the velocity of the interface, which is Vi, right. Okay. Moment that particular thing happens, what we get is, you can substitute this V1 relative as equal to, okay, V1 minus the corresponding Vi, like we did in the last time in the case of a momentum expression. So, this is the total expression that we get after substitution of this particular expression, this and the corresponding V relative also, V2 relative, right. So, what it tells you is that the shears, the stresses at the interface, okay, acting on the interface is basically nothing but the flux terms. Okay. So, the stresses is equal to the flux term, that is essentially what it means. Now, recall that this part of the expression is nothing but that m dot triple prime that we defined earlier in the case of continuity, right. So, this is what? This is the mass transfer due to phase change across the interface, right. So, what, and we also noted that n 1 is basically negative of n 2, that also we noted, right. So, what it tells you is that tau 1 in dot n 1 plus tau 2 dot n 2 becomes tau 1 prime minus tau 2 prime dot n 1. We are substituting n 1 is the same as minus n 2, right. Similarly, on the right hand side we can see this is the corresponding mass flux, right, okay, which we know if you go to this particular expression you will see that this is the corresponding mass flux expression. Let me highlight it here, right. So, that is the mass flux expression. Okay. So, and noting also that m 1 triple prime is minus m 2 triple prime, right. So, basically when we actually expand these two quantities, if you look at these two quantities, what these two quantities will look like is that m 1 triple prime into V 1 minus V I, that is the first expression, right, minus or rather plus here m 2 triple prime V 2 minus V I, right. But using m 1 triple prime is the same as minus m 2 triple prime. Okay. What we can do is that this expression will become V 1 minus V I minus m 1 triple prime V 2 minus V I, right. So, if you add these two quantities, this V i's will drop out and you will get this expression. Okay. And on the right hand side, on the left hand side we have the difference in the shear stress. Okay. Now, as we know, the total shear stress is given by P and the corresponding shear stress for each phase, right. So, just if we substitute this, what it becomes is it becomes P 2 minus P 1 into N 1, tau 2 minus tau 1 into N 1 or dot product of N 1 is nothing but equal to m 1 dot double prime multiplied by V 1 minus V 2. So, that is the interface condition that you will get if you deal with a interface from the momentum part of the interface, right. So, from the continuity part we got m 1 is a negative of minus m 2, right. Here we have seen that the difference in pressure across the interface plus the stress that is acting across the interface, the difference in stress across the interface is basically what is responsible for the mass exchange or the momentum exchange due to phase change. This is nothing but the relative momentum exchange due to phase change. Okay. Relative momentum exchange due to phase change. This is the net, you can say the net efflux of momentum due to phase change. Okay. Now, if for example, m 1 double if there is no phase change, say for example is happening, right. So, what we will have is P 2 minus P 1 into N 1 plus tau 1 minus tau 2 dot N 2 should be equal to 0 in the event of no phase change, right. So, the difference in pressure across the interface, okay, is that equal to the plus the difference in shear stress or stress across the interface is given by is equal to 0 if there is no phase change. This is the net efflux, right, of momentum, okay, due to phase change, right. So, this concept should be very clear, okay, that This is what happens, this is what the equation means. Similarly, let us look at the energy balance. Now, the total energy, mechanical and thermal energy balance at the interface, if you recall the original equation which contains two phases, this is a slightly bigger palette with a lot of terms, okay, but let us not be scared about it. We have done essentially the same thing. We have added the interface, we have taken out the interface, right, across the interface. This is basically the flux across the interface, right, and we have taken the added and subtracted it. Similarly, on the right hand side of the expression, okay, what we have done is that we have taken the this is the diffusion term, we have added the interface, we have taken out the interface, okay, over here. Sorry. So here if you look at it, so this is the expression that has been added, and the total heat release, of course, the internal heat generation of course remains the same. On the other hand, this is the work done by the stress, if you recall, that also has been added and subtracted, right, and there is a body force term because it is on the volume basis only, okay, it does not have any interface component to that, right. So, there are three terms that have been brought in. One is basically the flux term, okay, across the control surface, that means across the interface. There has been a diffusion term which has been brought in, okay, this should be negative actually, okay, and correspondingly or actually it will be positive, I am sorry, because this is negative, that transfers it to positive sign, okay. So, let me just, this is correct, okay. So, that part is correct, okay. So, this plus sign is correct because there is a negative sign in front of the heat diffusion term. So, when you actually subtract it out, it becomes a positive quantity, and similarly the stress term, that is the stress, that is the work done by the stress on the control surface, has been also added and subtracted, the interface term, right. So, we have added basically three terms, we have subtracted three terms, that is all that we have done. Okay. Again what we do, follow the same logic, convert the surface integrals to the volume integrals, right. So, this is the volume integral, okay, which looks suspiciously like the energy equation, and this is the corresponding additional terms that we have incorporated because of the interface, that is AI, right. So, because of AI we have added all these terms, right. So, similarly this term goes to 0, that is like your energy equation, right, that is the energy equation that we did. So, this is, so we are left with just the interface term, right. So, the energy balance in that, so again the, because this is an integral form, the integrand has to be equal to 0, right, the integrand must be equal to 0. So, the energy balance at the interface becomes this. So, that is nothing but this term in the square bracket, that is all, that is equal to 0. What does these terms contain? One is the flux term across the surface, okay, and the other one is the diffusion term, that is also across the interface, and then there is a work done term because of the stresses also at the interface, right. These are the three quantities that we have, okay. Again we set the reference velocity as the same as the velocity of the interface. So, once again this Vk relative becomes equal to V1 minus Vi, okay, depending on the phase that you are belonging to. So, this becomes the first term, okay. So, the first term wherever there is Vk relative, that becomes like this, right. So, if you look at this particular term now, this suspiciously looks like that m dot triple prime, is not that so? It looks like that m dot triple prime, exactly what we did earlier. So, that is what we have done, okay. So, m dot triple prime k means the mass flux across each phase because of phase change only. This is due to, why is it coming like this? Due to phase change, okay, that we already knew earlier, right. So, and this equation involves the internal energy component as well as the kinetic energy component, right. this particular term over here includes the corresponding mass, the heat transfer component, and this is once again the work done by the stress, by the normal and shear stresses. That is what we have said over here, advection, heat transfer and work done by normal and shear stresses. So, that is the balance for the interface, right. So, across the interface there is a term which is advective because of this change in the phase, because of change in phase. Okay. There is also a diffusive transport and then there is a work done transport. Now, for example, if in some ways there is no phase change, okay, what you will have over here is that your Q K double prime dot N K minus N K dot K relative, and this will be like V K relative is equal to 0. That is what we are going to get, right. Okay. If there is no mass component, of course, this is summed over the k equal to 1 to k equal to 2, right. So, if there is, once again, the dissipation terms are not that important, you can further reduce it further. So, it will essentially boil down that the diffusion of heat across the interface has to be equal to 0 from both the phases, right. Okay. So, that takes care of the interface conditions for the energy. Now, similarly, if we look at the species balance equation now, the conservation of species mass, for example, for a control volume that contains two phases separated by an interface, once again, because the species balance is up next, right, that is what if there are multi component systems. So, we are doing it for the ith species essentially. Okay. Once again, what you do, standard thing, we add this, we take this out. This is basically nothing but the flux component, okay, and we do the same thing for the diffusion component like we did for the heat, right. We had this component for the heat. Where did we get it? We got it in a method similar to this, right. So, here also we add the diffusion across the interface. Of course, here you do not need to do anything, this is because simply this is the species that is created or the production or the sink term, okay. So, following a very similar process, we divide it into two parts, right. This part is equal to 0. So, this part automatically becomes equal to 0. So, that means this particular portion becomes equal to 0, right. Once again, the integrand, we once again set the reference velocity equal to the interface velocity, and we make that the integrand is actually equal to 0. So, this takes into account that the integrand has to be equal to 0. Okay. So, the reference velocity is equal to the velocity of the interface. Okay. So, we ultimately get to this particular expression over here, okay, which is nothing but V k minus V I plus whatever is the diffusion component of the same, that is equal to 0. Okay. And if you look at this expression, what is rho k I? Rho k I is basically rho k I by rho k by rho k is basically omega k I, right, something like that. So, if we incorporate that definition over here, this is the expression that you get. So, it is basically the mass fraction into the corresponding mass transport of the ith species. This is the total transport of mass from the kth phase to the corresponding adjoining phase, right. Okay. And this is basically the mass fraction for that particular ith species and summed over all the phases, and the corresponding flux of the ith species in the kth phase, okay, across the interface, this has to be equal to 0. Okay. So, the two terms in the bracket represent species transport due to phase change, this is the first term, and diffusion across the phases due to the gradients. So, there is a phase change due to the species due to the phase change, there is a species transport, and there is also a species transport due to diffusion across the phases due to such gradients. Okay. So, this part should be clear now that this is what we have, okay, for the species balance. Okay. So, these are the three conditions or the four conditions for continuity, momentum, energy, and now species. And then can be various special forms of each, but essentially you should always remember there is a component always that is associated with phase change, and then there is a component that is associated with diffusion. That is what the two things are, right, in the case of species. Okay. Now that we have done up to this particular portion, okay, let us look at a couple of more things in a slightly more details. Okay. Imagine a system which is very complicated, right, that there may be like the first day's lecture that we gave, that there were a lot of bubbles say distributed, there may be complicated shapes, okay, there may be multiple intertangled interfaces, okay. So, those kind of things could be there, okay. There may not be a clear cut separation between the two phases or between the phases, not just two, any number of phases in a multiphase system. Okay. So, in order to the other formulations that we so far did always considered the interface is kind of easily tractable. That means you can track the interface, correct. In many of the real life cases that may not be the scene at all. The interfaces can become corrugated, they can become very complicated, there can be lots of things. Okay. So, this is not always possible for cases with multiple interfaces. Interfaces, to track the interfaces itself can be a literal nightmare. So, the macroscopic aspects of the, in those cases however, we still want to analyze a multiphase system, right. So, what can we do? We can either track each and every point, we can take a flow and we can track the interface by using different types of methods like level set, there are other types of methods also. You track the interface, then you let the interfaces actually evolve. So, that is a very complicated and onerous task. But however, macroscopic aspects of the multiphase flow may be more important for the design and operation of a multiphase system. So, you may not need all those information. So, if you can on the other hand develop some kind of averaging techniques which gives you the mean values of the flow, the thermal properties, and eliminate the need to explicitly track the interfaces, then that would be like a great thing to have, that would be a great tool to have. Okay. So, what are the ways by which, because we can write governing equations, not a problem, but if the problem involves such complicated interfaces, it may not be always feasible to track the interfaces and to analyze the problem, okay, in a very simple way. Okay. So, one such averaging will be the Eulerian averaging scheme. What does it do? Eulerian averaging is the most important and widely used averaging because it is consistent with the control volume analysis, right. So, whatever we did, that was like an Eulerian kind of a framework or field concept. Okay. So, if we take any generalized function phi, say for example, where phi is a function of x, y, z and t, the 4 dimensions, it is a function of space, it is a function of time. So, the time average is obtained by averaging the flow properties over a certain period of time, right. So, when we talk about average, that phi bar, okay, it is basically averaged over a particular time, this time slot, this is delta t. Okay, over a particular time it is averaged. Okay. If we talk about Eulerian volumetric averaging, on the other hand, it is usually performed over a volume element around a point x, y, z. Okay. So, it is performed over a volume element, there is a point say x, y, z in space, right, and so it is performed across one such volume. If I put this particular figure up, you will see. So, this is the volume element delta V. If you look at it, it has got those individual patches which are basically the different phases. So, this is one phase, this is another phase, there can be other phases also, this is another phase, this is another phase, right. All these are different phases, right, and this is the volume element that we are talking about. Okay. So, inside this volume element there are these small elemental areas of the different phases and they can be distributed in whatever way that we want. So, basically you can see that we are losing the resolution over this window. When we actually do the averaging, out, when you average whatever properties that you want to average, that may be mass, energy, whatever it is, right. If you want to develop this concept, then if you do it over this elemental control volume, whatever is inside this, okay, whatever is the individual property variations within this, right, that is kind of averaged out. Got it? So, we are not looking at probably gradients inside, okay, it is like completely averaged out these things, right. So, if you look at this particular expression, so it is performed across a volume element around a point xyz. So, I hope that makes sense now, that what I am talking about. Okay. So, the total volume element is basically the individual volume elements that are occupied by each of the phases, right. So, if you look at this, these are like those individual volume elements, right. So, this is like this dVk or delta Vk, right, that is like delta Vk, right. So, these are the individual volumes, okay, of each of the phases, and this is the volume fraction of the kth phase. So, that means if you look at this, say this is phase 1, phase 1, phase 1, phase 1, phase 1, phase 1, all these areas, right. So, you calculate the volumes of all these phases, right. Okay. So, say you get something like some delta V1, if you divide it by delta V1 plus delta V2, right. So, that is what actually gives you epsilon k, or rather here so actually sorry, this will be like epsilon 1, but in a normal case this can be written as Vk summation of delta Vk, k equal to 1 to whatever. Here we are taking two phases, that will be like epsilon k. Got it? So, this is like what we call the volume fraction. Volume fraction of each of the phases. Got it? So, the volume fraction of each of the phases is basically what we are defining over here, right. Now, if we sum total of all the volume fractions should be equal to 1 by definition, it has to be less than 1. So, there can be any number of phases present, for example, here there are pi number of phases. So, if there is a volume element delta V which has got phases of 1, then phases of 2, and phases like 3, okay, you can put that pi into whatever is the magnitude 3, 4, 5, whatever it is that you think it is going to be. Got it? Okay. So, if you look at this, this is clear, it is only done for two phases, is equally applicable for any number of phases that you can think of. So, I am giving you an idea of what this volume element should be, right, and what are the individual volume fractions should be, and how each of the elemental volumes are actually defined. Okay. So, in the next lecture what we are going to do is that we are going to basically look at how this Eulerian averaging is performed. Okay. So, that we are going to do in the next lecture.